Hello maths fans, Dr. Tom Crawford here at the University of Oxford, and today we're looking at the Gram-Schmidt process. The Gram-Schmidt process is a procedure that you can follow to obtain an orthonormal set of vectors within an inner product space. If you do not understand either or both of these terms, then I strongly recommend going back to the last video in the Oxford Linear Algebra series where we looked at inner products, as you are going to need to be familiar with them in order to follow what we'll be discussing here. To apply the Gram-Schmidt process, you start with a finite set of linearly independent vectors from an inner product space. So, Gram-Schmidt takes as the input a finite linearly independent Li set, and it will output an orthonormal set. Just to make sure we are all on the same page, recall the definition of an orthonormal set of vectors as follows. We say that v1 up to vn is orthonormal if the inner product between vi and vj, so any two members of the set, is equal to delta ij, where the delta function gives you 1 if I is equal to j and 0 otherwise, so i.e. if I is not equal to j. So Gram-Schmidt, start with our linearly independent set, which must be finite, and then it will output, having followed the steps of the algorithm, it will output an orthonormal set, which means that taking the inner product of any elements within this set can only give you 1 or 0 according to this definition. Now, in the previous video, we actually saw how an orthonormal set within an inner product space is in fact linearly independent. So the Gram-Schmidt process is actually playing the role here of the converse. It's telling us that if we start with a linearly independent set, we can in fact get the orthonormal set, and importantly, it actually gives us an explicit way to calculate exactly what that set is. So not only does it tell us that such a set exists, starting with linearly independent, we can always get orthonormal, it actually gives us a recipe to follow to calculate those vectors, those orthonormal vectors, explicitly. So here are the steps of the Gram-Schmidt process, which I'm going to write as shorthand GSP. So as I've written at the top, we begin with our linearly independent set. Let's call it u1, u2 up to un. And step 1 is simply to take our first vector, u1, and what we're going to do is define v1, our first orthonormal vector. That is just going to be given by the vector u1 divided by its norm. So here we are normalizing the vector, which means that when we now take the inner product of this thing with itself, we will indeed get 1. So we're making sure that this property up here is satisfied. Now, anytime we do a division in any kind of calculation, you should be thinking, could the denominator be 0? And we're actually okay here because the modulus of u1, so where the modulus of u1 squared, we actually say is the inner product u1 with itself. And of course, by the fact that this is an inner product, we therefore know it is positive definite, so we know that this is greater than or equal to 0 and equals 0 only when the vector itself is 0. And of course, the 0 vector would not be included in our linearly independent set, so by positive definite, we are okay by dividing by the norm of u1. Now for step 2 in the process, and in fact all preceding steps, we are going to form an intermediate, which we're going to label with w, and then once we've calculated that, we're going to normalize to get our v, our orthonormal set. So what I mean is as follows. Step 2 is we form the intermediate W2. And the way we do this is we take our second linearly independent vector, U2, and then we subtract off the component of U2 in the direction of V1. And the way we get that is we subtract off U2 in the product V1 multiplied by V1. So the inner product gives you a scalar, so we have a vector minus a scalar times a vector, so we're still within the vector space, so everything is okay in terms of our vector space axioms. So this is going to be our intermediate. Again, we have taken our vector U2, we've then projected onto the part of it that's in the V1 direction, and then we've taken that away. So that's actually going to help with this orthogonality, as we'll see in just a moment when we investigate this a little further. But at this stage, we calculate this, and then once we form the intermediate, we then define V2 to be the intermediate divided by its own norm, again to ensure that when we take the inner product of V2 with itself, we're going to get 1 and satisfy the orthonormality. Now let's just take a moment to look at this intermediate vector a little more closely to try to get a feel for what is going on and in fact why this is going to work and give us the orthogonal relationship between W2 and V1. So what we're doing here is forming this intermediate, and then all we're doing is normalizing it. But even before we normalize, W2, if formed correctly, should in fact be orthogonal to V1. That still has to be true. Their dot product is going to be 0. That will be true whether or not we divide by the norm. So if we actually take W2 and now calculate explicitly its inner product with V1, we should get 0 if what we've done is going to be correct. So we can check that. So let's calculate W2, comma, V1. So we can just substitute in the definition, and what I'm going to do is just use the linearity as I do so, just to help a little bit. So we're going to get U2 with V1 from that first component. And then what we want is minus this thing here, remember, is a scalar, so it comes outside of the inner product, so it's minus U2 V1, which is outside of the inner product. And then the inner product we're left with is the vector component V1, which is now with itself, with V1. So we get a V1, comma, V1. So again, just to sort of go over that, all I've done is substitute for W2 into the inner product. Now there are two pieces here, and you can sort of, if it helps, think of it as this is basically U2 minus some alpha times V1. It's just two vectors where we're subtracting alpha of the second one from the first one. So now, using linearity, which is one of the properties of our inner product, I can split this up into the first piece with V1, and then I subtract off, this thing here is playing the role of alpha, and then I'm left with a V1 inner product with itself. But of course, we have already normalized V1 up here, so this is just 1. So what we're left with is U2, comma V1 minus U2, comma V1. So we are going to indeed get 0, put a tick there, the orthogonality relationship there is going to hold. And it worked precisely because we subtracted off alpha lots of V1, where that amount, that alpha, had to be U2 V1 to make everything balance. Step 3 of the Gram-Schmidt procedure actually just tells us to basically repeat step 2, but for the next vector in our list. So here, so we sort of say repeat for each vector. And what we mean by that, because there is a very slight sort of modification you have to make at each step. So we're going to repeat for each vector. So e.g., for the next one, we form the intermediate. So we would form w3 is equal to our third vector. Now we subtract off the components of u3 in the directions of the vectors we've already defined. So we want to subtract off any part of u3 that's in the v1 direction and any part of u3 that's in this v2 direction. So we want to do u3 minus, let's subtract off the bit in the v2 direction. So that's u3 v2, v2, and then let's subtract off any part of u3 that's in the v1 direction. Where again, the amount of v2 that we subtract and the amount of v1 that we subtract is this projection in a product in both cases. So this is going to be our intermediate, and after we've done the intermediate, we then say, and once we've done that, v3 is then just going to be w3 divided by the modulus of w3. We continue in this way, so next we would go to w4, which would mean subtracting off 3 previous parts in the directions of v1, v2, and v3, with again the same scalar in front of each of those. And eventually we would get to the end. So we would eventually get to defining wn, our intermediate, and this would be un minus, now there's going to be a sum of n minus 1 pieces, and each of those pieces has a coefficient which is un multiplied by vj multiplied by vj outside the inner product. And that's going to be from j equals 1 up to n minus 1. So again, we're just going to subtract off the part of un in the v1 direction, subtract off the part of un in the v2 direction, all the way up to the part of un in the vn minus 1 direction, and then this is wn, and finally we say that vn, our last vector, is wn divided by its modulus. And that completes the Gram-Schmidt procedure. Now, I did mention earlier that we would look at this concept of projection and subtraction of the previous vectors to get us orthogonality. We're going to look at this in a little more detail with an explicit, concrete example looking at the 2D Cartesian plane. As I know for me at least, it is very helpful to visualize exactly what's happening here. And hopefully, if I can convince you how this works in 2D with our usual Cartesian plane, xy plane, if I can show you why that works and how that works, you can then sort of see how that might generalize into higher dimensions. Unfortunately, I cannot draw 3D and higher very well on this board, which is why we're going to focus on the 2D case, but it will generalize in exactly the same way. So let's suppose I have 2 linearly independent vectors in the 2D plane, and they are going to be given by 1, 0, and some other vector, let's call it b, and as of yet, b could be anything, as long as it's linearly independent with our vector 1, 0. So let's suppose we're going to call b x, y. It's a point in the plane, but we know that this is a linearly independent set of vectors because, of course, that is what we need to be able to apply Gram-Schmidt. So, according to our steps, step 1, this tells us how to define our first orthonormal vector, but this is already done. So 1, 0 is already normalized, so that's fine, already has length 1. Now, step 2 is going to tell us to compute this particular product. Now, before I do that, I'm just going to draw a diagram of what's happening here, because it's going to be really helpful, again, to understand what we're doing in step 2. We have a horizontal vector, which is 1, 0. That's going to be along our x-axis. Let's label that the vector 1, 0. And then we have another vector b. So it's going to some general point x, y. Let's put this vector up here, like so. And this is going to be our vector b, which is going to be at the location x, y in the 2D plane. Okay, now for step 2, we need to compute this intermediate. So let's start with that. So W2, the intermediate, is given according to the Gram-Schmidt procedure. Follow the algorithm. It's U2, which is b, so it's our vector b, minus the inner product of b along with our first vector, which is, I will just call it v1 for now, but we will substitute in just a moment. And then we multiply by v1. So this is now going to look like the vector b, well, that's xy. Then we subtract off the inner product of two vectors. Now, we're in the 2D plane, so the inner product here is the dot product, would be the standard one to take. So let's take the dot product. So this is now b dotted with v1, so that means we do, I'll put this in square brackets, b, which is given by xy, dotted with 1, 0. And then that gives us a scalar, which then multiplies the vector 1, 0. So again, computing this explicitly, we can say, well, that is now equal to x comma y minus, so we've got xy dotted with 1, 0. But 1, 0, that just gives us x times 1 plus y times 0. So that's just giving us x. So that's giving us minus x multiplied by 1, 0. So this bit in here just equals x. So now I've got xy minus x times that. Well, that's just the same as xy minus x0. And so we can see now that we lose the x. So the x bit disappears, and what we're just left with then is going to be 0 comma y. So what we've done through this projection and subtraction aspect of the Gram-Schmidt procedure, what we've done here is actually subtract away the x component of our general vector b. We've removed all of the component of that was in the other vector, v1. So b itself has two components, where the first one, this is the amount of v1. Now this is of course quite specific to this example, where v1 happens to be exactly the x-axis. But this works more generally. So what we're doing again is we're subtracting off the amount of b that's in the direction of our other vector so that we can make them orthogonal. We're removing that component. Because now, of course, this is W2, so we can say, well, V2 then is just W2 divided by its norm, but W2 is 0y, so the norm of that is actually just going to be square root of y squared, which of course is y, so we just end up with 0, 1 to be our other orthonormal vector, which of course is exactly what we expected. So what we've done is actually move or rotate b to actually move like so. It's moved that way, and now we end up with the 0, 1, and now we've got our two vectors that are at right angles to one another. They are orthogonal and they both have length 1, which are the two properties we need for it to now give us an orthonormal basis. So that's Gram-Schmidt. We started with a pair of linearly independent vectors. We apply steps 1 and steps 2 of the algorithm, as there are only two vectors to orthonormalize, and we end up with our orthonormal set 1, 0 and 0, 1. As usual with the Oxford Linear Algebra series, there is another video explanation available to all of you via ProPrep, which you can access for free by signing up for a 30-day free trial using the link in the video description. ProPrep is an online resource which provides video tutorials for students looking to improve their skills in STEM-based subjects. Alongside an alternative explanation of the steps in the Gram-Schmidt process, there are 4 exercises, each with full video solutions. The first 2 extend the example we've just looked at of the Cartesian plane to 3 and 4 dimensions. Next, we have an interesting example on the polynomial inner product space, where the inner product is defined via an integral. And finally, we have an example involving matrices with another type of inner product, this time defined using the trace of a matrix product. Just click the link in the video description to get started with your 30-day free trial right away. Now that we've outlined the procedure and hopefully have a better feel for how and why it works, let's work through a final explicit example. We've already looked at plenty of Rn examples, both here and in the previous video on inner product spaces. So let's do one in the polynomial inner product space instead, where the inner product here is going to be defined as follows. So if I have my 2 polynomials f and g, then we say the inner product of them is going to be given by the integral from 0 to 2. Then we have a weight function x, f of x, and g of x. And of course, we integrate with respect to x. So this is slightly different to any of the previous examples we've seen, because now we have this weight function x inside the integral. Now, I'm not going to go through the details to show that this does indeed define an inner product, but it is a highly recommended exercise for the viewer, particularly for those of you who are still getting to grips with what we covered in the previous video on inner product spaces. So you want to check that this is indeed linear, it's symmetric, and positive definite, according to the inner product definitions from last time. But what we are going to do here, because it's the focus of the video, is actually to construct an orthonormal set for this inner product space. So we're going to start with a linearly independent set, and I'm going to suppose that my linearly independent set is going to be 1 and x plus 2. Again, I'm not going to check that this does indeed define a linearly independent set. Again, you can check this for yourselves. What we want to do is take these 2 vectors, so let's call this one u1 and this one u2, take these 2 linearly independent vectors, and we want to follow the Gram-Schmidt procedure and hopefully get something at the end, which is going to be an orthonormal set or an orthonormal pair of vectors. So step 1 is to normalize our first vector. Now you may look at this and be like, oh, it's already normalized, it has length 1. But that would be using the traditional definition of length. Here, our length is defined by this inner product, so we have to check that is indeed the case. So, step 1, we want to compute the norm of 1 using this inner product, and then of course divide by that to get a normalized vector. So we want to compute the inner product, again using this definition as written on the board here, of 1 and 1. So what's that? That's the integral from 0 to 2 of x, our weight function, multiplied by 1, multiplied by 1. So we're integrating x between 0 and 2. So that is x squared divided by 2, evaluated between 2 and 0. So we're just going to get 2 is going to be the answer. So therefore, to normalize our first vector, we need to say, so therefore, v1 is actually going to be defined by the first vector, 1, divided by the modulus of that vector. Now, what we've calculated here is actually the modulus of u1 squared. So we have to remember, and this is important, lots of my students miss this, have to remember to square root this answer. So the modulus of u1 is going to be the square root of 2. So this is in fact going to be our first orthonormal vector. We now continue with step 2, which is to first define our intermediate. So step 2, we are going to therefore consider our W2, which is going to be equal to U2, which is x plus 2. So we have x plus 2, and then we subtract off the inner product of x plus 2 with v1, which is 1 over root 2. And then we multiply that whole thing by 1 over root 2. So I'm going to simplify things a little bit here just to help me out. If I take this 1 over root 2 inside, that will just give me a 1 over 2 inner product. So this is going to now require me to calculate. So we compute, therefore, the inner product of x plus 2 along with a half. So again, using our definition up here, that's going to be, pull the half out, and we've got the integral from 0 to 2 of x times x plus 2, so that's x squared plus 2x with respect to x. So we, again, leave the half outside, we do that integral. That's going to be x cubed divided by 3 plus x squared, and that's between 2 and 0. So that's going to give me a half multiplied by 8/3 plus 4. Okay, so that is the same as 4/3 plus 2, which is 10 over 3. Do I agree with that? 4/3 plus 2 is indeed 10 over 3. Yes, so that's 10 over 3. Okay, so we now go back and plugging this up here. So therefore, W2 is x plus 2 minus the thing I just computed, so minus 10 over 3. So that whole thing then is actually just going to now give me x plus 2 minus 4/3. Minus 4/3. So that one is W2 here, which is not yet the answer, of course. This will be orthogonal to our other vector 1 over root 2, but is not yet normalized. So we have W2, we need to normalize it. So carrying on over here, we need to compute W2 with itself. So the modulus of W2 squared is the inner product of W2, W2. So again, according to our definition, we've got x minus 4/3 with itself and with this x. So we actually want the integral from 0 to 2 of x times x minus 4/3 squared. Okay, dx. So that's going to be the integral from 0 to 2. I'm going to do the square inside the bracket. So that's going to give me an x squared minus 4/3 x minus another, so minus 8/3 x. And then it's going to be plus 16 over 9. And then all of that square bracket is multiplied by x. So that's actually an x cubed, that's an x squared, and that's an x dx. Now we can do the integral. So again, if I just kind of put a little arrow down here, the board's getting quite crowded. So this is now going to be equal to, what have we got? We've got x to the 4 divided by 4 minus 8 over 9 x cubed plus 16 over 18 x squared between 2 and 0. So putting all of that in, that's 2 to the 4 is 16, so 16 over 4 is 4, minus 8/9, so minus 64 over 9, and then plus 16 times 4 is 64, so plus 64 over 18. So that's 64 over 9 times a half, is what that is. So it's 4 minus 1 lot of 64 over 9 plus a half of them, so it's 4 minus a half of that. So it's equal to 4 minus 32 over 9. But that, of course, simplifies to be 32 over 9 is, oh wow, wait, no, make that 36, that's 4 ninths. Haha. The 4 is 36 over 9, that's what I've done in my head. So it's 36 over 9 minus 32, so it's 4 ninths. All right. Whew. So the value of mod W2 squared is 4 ninths, so we have to divide by the square root of that. So again, I'm going to squeeze it over here. Final step, a lot of work in this one. Therefore, the modulus of W2 is the square root of that. So that's 2/3, which works out really nicely. And so therefore, finally, we can say V2, our final vector here, is going to be x minus 4/3. And we want to divide the whole thing by 2/3, so multiply the whole thing by 3 over 2. So 3 over 2 gives me 4/3 times 3 over 2. So that's going to give me 3 over 2x minus 2. I believe is going to be my final answer. So I think my second orthonormal vector is 3 over 2x minus 2. My first one is 1 over root 2 over here. And of course, as you might have guessed, I'm going to set this as an exercise for all of you watching to check my working. So if I have done this correctly, and I have certainly followed the steps of Gram-Schmidt, but if my algebra is correct, V2 in a product V1 should give you 0. V1 in a product with itself should give you 1, and V2 in a product with itself should give you 1. So again, exercise for the viewer, check that those 3 things hold. That brings us to the end of today's video, but before you go, don't forget to sign up for your 30-day free trial of ProPrep using the link in the video description. Thank you everyone for watching. Please do remember to subscribe to the channel if you've enjoyed the video, and I'll see you all very soon. Take care.